Okay, it's 5:25, so let's get started. Feel free to pick up your tests. There are fire hazard at my house. Please take them from me. Internalize all the feedback. In general, this test was way better done than the first one. I think either every single person did better than their first midterm, or they about tied their first midterm. So there wasn't anyone who did significantly worse than their first one, which I was very happy about. So I posted all the scores and everything online. Any questions on the second test? So when's your final exam?
Wednesday.
Not this Wednesday, but following Wednesday. So
Will there be lecture after the exam?
there will definitely be office hours after. No. So the course ends at the final exam, as you might expect.
How long is the final?
The entire period, 125 minutes, all the way through. Yep. So I kind of want to show you the. All right.
It's beautiful.
It's super beautiful. Let's try that again.
The zoomed out view of all the questions on the exam. What?
Okay, well, let's.
So quiet, it's incomplete.
I like that humor. All right, well, I guess it's not going to work today. So what I was going to show you, you can come during the break if you like. I'll show this again on Monday, but the way that the final exam will work, I have an announcement already on this, is that it's going to be 40 multiple choice and 40 true-false. And there's no like proofs or anything like that, it's just multiple choice true-false. A perfect score on each of the two parts is 35. So essentially there's 5 bonus of each of the multiple choice and true-false. So what you're going to get are these 2 sheets, which is basically what we're going to grade off of, where you'll be putting your multiple choice and your true-false answers. Actually, it's true, false, and open answers, because there will be some questions that no one knows the answer to, and so you'll have to say either it's true or false, or no one knows the answer. So basically on this stuff, yeah.
Does that mean we don't have to give our description? It's suggested.
Yeah, it's just literally one. Yeah, so you'll be writing at most 80 characters.
Oh,
Yeah.
So just out of curiosity, what is open? Would you just put like, oh?
Yeah, it's on the thing, which I can't show you because the thing's down. But so like for the true, false, open, for example, you write T if it's true, F if it's false, O if it's open. Multiple choice, each question will have 5 possible answers. You write one of the 5 answers. That's it. Yep. So shouldn't be too hard, right? I guarantee you, like, the major parts of every part of the course will appear on the test, so it's not like anyone will study something and they'll be like, oh, that was never tested, so everything will be tested. Yeah.
It's the same like node policy?
Yeah, everything's exactly the same. Yep. Except it's now the entire time versus 75. What was I going to say about this? Oh, in addition to these 2 sheets, you're going to get 2 packets, one of which contains the multiple choice questions, and the other one contains the true, false, open questions. So you'll hand everything back, and then the course is over. Any questions about that? Yeah.
Is like the multiple choice weighting one to true or false?
Nope. A good question. They're weighted at 5 points every question. Multiple choice and true, false, all exactly the same. Yep. And so Dylan will grade one of them, and I'll do the other, so that because there's a short time frame to get the grades in, because I have to get them by Friday on, although that's technically not true, but I should get them by Friday, 2 days after the test. So, other questions about the final? I'll talk more about this on Monday. Yeah.
What's like the estimated runtime for like your test run for the test to like do it complete?
I'm not sure what the question is.
Like, did you try to complete the test yourself?
I haven't even made the test. I just made the answer sheets. So I'm going to try to estimate it at 1.5 minutes a question. So that'll put you at 120 minutes, and so you'll have 5 minutes of brief and riff.
5 minutes Ph.D.
Yeah.
quality student.
Yeah. Well, technically, you could write just C, and you'll almost be certain to get 20% of the answers right, based on a in expectation. But in expectation. But that doesn't say that you will get that. I'm just, yeah, depends on how it's made. But any other questions about the final test? So I put this announcement about this too. So I'm going to cover NP completeness today. On Wednesday, we're going to do space complexity. So we're doing time complexity now, and we'll talk more about space complexity. And then Friday will be kind of a grab bag lecture about like recent techniques to solve certain problems. So like a bunch of techniques to try to separate P and NP, or some problems relating to some of the other classes we'll talk about. So it'll be a really cool lecture. So I hope you don't miss. Yeah. Yeah, we're gonna get to that. But any other questions about the test? Next Monday is a final exam review session. So there'll be no new material next Monday. Any last questions before we dive into stuff? Okay, so what were we talking about last time? P and NP. So what does P mean intuitively? Not the formal thing, but what does it intuitively mean? Yeah, polynomial time, efficient algorithms to solve problems. So, so this is, remember, is the set of all languages decided by some TM in polynomial time. So remember, that's polynomial in the size of the input. So as you might expect, if you provide more and more input, the runtime of the machine should go up in general. But it's just, we have a polynomial time upper bound on how long the Turing machine runs for any possible input. And then what was NP, the easier method? You could just say, oh, this is just the non-deterministic Turing machine version of NP. But what's the more intuitive definition for it? Yeah. Yeah, we have this certificate thing, right? So in other words, we can verify whether a solution is in the language or not. So if you give me a prototype solution, you can also give me a proof, a short proof, of whether or not that machine belongs in the language or not, and I can check that efficiently, okay? So NP is the set of all languages that I'm just going to be even more informal by just saying that can be verified in Polytime. Verified by that certificate. So, like, for example, the Clete problem that we talked about, which is, does there exist a complete subgraph on k nodes in this graph? One of the certificates is you give me the k nodes, or I give you the k nodes, and then you can verify yourself whether or not every one of the k choose 2 edges exists in that graph or not. If all of them exist, then I just found out, hey, there is a complete subgraph in there. There is a k-clique in there. And if you find that one of the edges is not there, then you say, no, that's not a k-clique. So you can verify that in polynomial time. Does that answer your question? Okay. Any other questions about these two? So purely based on the definitions, we found out that P is a subset of NP because the verification here can just be running the algorithm itself, the polynomial time algorithm for whatever problem you have that's in P. And so the verification or the certificate would be the actual running of the algorithm itself. And so that's how we found that out. But of course, we don't know whether or not these two are different or not. So we don't know any example of any language that we can prove is in NP but not in P. Okay? And so basically the rest of the class is focused around questions like this. But any questions so far? Okay, well, suppose that, so most people, including myself and maybe most of you, think that P is different from NP. So there is we believe that there is a language that's in NP but not in P, right? So let's just go off of that assumption for now. Well, how would you even find one of these languages? Let's just suppose there is one. How would you even find it? Or what would be a good heuristic as to say, this is a candidate one? Well, if we can find, so I'm going to be informal and say that if we can find the hardest problem in NP, could that be the one that separates P and NP? Whatever by hardness I mean? Yeah, that seems intuitive, right? The one that takes the longest amount of time to solve. Okay? Well, so what we want is to find the, or a hardest, whatever that means, problem in NP. And if we can find one, then maybe we can say something about whether P and NP are different based off of this problem, or if there happens to be more than one, which there are, if there's more than one, then we can say something about, okay, maybe these are a set of candidate problems. Well, how would I define what hardest in this sense means? So let's go back to formal. How would I define hardest? Complexity, yeah. What could be another way? Well, suppose that whatever this problem is, suppose, for example, that it's in P. It actually is all the way down in P. Then what should the relationship be between P and NP? Should they be the same now? Or should there be some other problem that's outside of P, but still in NP? So let's make this a diagram. So this is what we believe to be the world right now, right? So we say that we believe that there's a problem like this out in NP, but not in P. But suppose, for example, that this is one of those hardest problems, whatever that means. Then suppose, again, for example, that problem really is in P, this hardest problem in NP. Then what should P and NP be? The equal, right? So that should be a way to define what hardest means. So if this is true, then P equals NP. Or that's what we would want it to mean. Okay. So what other terms about NP did we define last time? Well, the verifier, but we talked about this non-deterministic computation, right? Well, we got to think, well, if I can solve this hardest problem then in polynomial time, then I can solve any NP problem in polynomial time as well, right? So what kind of relationship between these two problems does that sound like? We've kind of seen it before. It kind of looks like a reduction, right? If I can solve this one at all, say decidable, then I can solve this one, which would show it's decidable. Same idea here. If I can solve this hardest problem efficiently, say in polynomial time, then I can solve any NP problem at all in polynomial time as well. So that's actually what we're going to define next. So we say a language L is NP. So this is also a widely misused term. So L is NPhard if, well, what does this mean? It says that if I can solve L efficiently, then I can solve any problem in NP at all efficiently. But that means that looks like a reduction. But can I just allow any reduction here? Like I can take any NP problem and I can just do whatever reduction I need to get to this problem L? What should I guarantee about the reduction? What if this reduction, for example, takes more than polynomial time? Then I might as well just solve L efficiently by itself, right? So we gotta guarantee that the reduction does not take longer than the thing we're trying to bring this language down to P. So we need to have this reduction take polynomial time. Okay? So this is what is called a polynomial time reduction. So if for any problem you want be an NP, so any problem you want to solve, there is a polytime reduction from B to L. And this is denoted same notation as before, but I put a P on the less than and equal symbol. So that just denotes this reduction takes polynomial time instead of just any arbitrary reduction. Okay? Yeah.
Like, the notes have that backwards, the L and B. Am I reading wrong? Might be.
Yeah, that's it.
Yeah, the notes are wrong. Yeah, I'll fix that. You get a bonus point. But any other questions about? So this is correct. The notes are not. Any questions about that definition? Does this say anything about whether L is an NP? No. It says that B is an NP. That's definitely true. But it doesn't say anything about whether L is in NP. Remember ATM, that undecidable problem? It's NPhard. Okay? So many languages are NPhard, even undecidable ones. So what would we need to do to try to separate P and NP? Well, what we need is to have a language in NP to be NPhard. Because NPhard gets us the right idea about solving problems efficiently, then I can solve any problem in NP efficiently. But we need to also guarantee that this language L is also in NP. So we say L is NP complete if L is NPhard and L is in NP. So the completeness just, the word itself just means it's complete for the class NP. It's the hardest, quote unquote, problem for the class NP. And you might imagine that there's, for a different complexity class, there's a complete and hard version for those as well. But we're going to only talk about NP complete today. Any questions on that? Yeah.
Two problems are already NP-hard, and you're trying to do Polytime reduction between both of them. Is it just like trivial?
Oh, good question. So this is actually quite an important result, but it's actually pretty simple to prove. So if A poly reduces to B, and which one is it? And A is NP complete, then if B is also an NP, then B is also NP complete. So if we have an NP complete problem, then if I can find a reduction, a polytime reduction, to a problem that I want to solve that's also in NP, then this resulting language must be NP complete. Why is that true? Well, what does NP completeness say? it says, ignore the NP part for a second, just the NP-hard. If any language, so A is NP complete, anything in NP must polyreduce to A, right? Because by definition, A is NP complete. Well, does that mean anything could reduce to B? Well, think about it. If I do 2 polytime reductions, could I do that in polynomial time?
Yes.
Yeah, well, think about it. If I do the first polynomial time reduction, then maybe whatever the result I make could be a lot larger than the original instance, but it's only polynomially larger. So if I do another reduction, again, it might be polynomially larger, but what is a polynomial times a polynomial? Also a polynomial. So in fact, if A reduces to B and B reduces to C, then A reduces to C. This is a transitive reduction here. So sometimes reductions are not transitive. This one is, which is kind of nice, what we need it for. So if I can find an NP-complete problem and do a reduction to a known problem that's in NP, then I can say that that one's NP-complete too. Question is, can we find an NP-complete problem? Do we have any yet? Nope, we don't got one. So we're going to take a small diversion, and then we'll come back to this. But the diversion is to introduce the first problem that will prove NP-complete. And it's actually the first NP-complete problem to be ever proved by anyone anyway, which is kind of interesting. So this problem that we're going to talk about is pretty much the backbone of every single NP-completeness result that you'll ever see. In fact, even for me, some of the best results that I have for my own research come from this particular problem and finding fast algorithms for this problem, even though we haven't found a polynomial time algorithm for it. But this particular problem is actually very important to the whole field. So anyone remember what a Boolean is? Yeah, true, false. So what we're going to be working with are Boolean formulas, okay? So formulas that have variables, and those can be true or false. So let's just introduce this. So a Boolean variable can take on the values 0 or 1. So not too surprising. So what are the most common Boolean operations out there? And, or, and, not, or negation, yeah. So we're going to be working with and, or, and not for operations. And we're going to denote and by a wedge. We're going to denote or by a V, and not by either negation with the little symbol, the little L symbol on the front, or if X is the variable, we'll put a bar over it. So that just means the negation of that variable. Or if X is a formula, for example, it could be the negation of the entire formula. So if, for example, if we want to look at the formula x1 and not x2, and then that ORed with x3, and then and with x4 not. Something like that. So that would be a Boolean formula. Is this class confusing? So it's about to get a lot more confusing. Not really, but who remembers CNF? So what does CNF mean as far as we know it? Chomsky normal form. We're going to see another CNF. So we're going to say that a clause is a disjunction, and English for that means or, of what are called literals. So a literal is either the variable itself or the negation of that variable. So each one of these are all literals. But the variables are x1, x2, x3, x4. So the literal is either you fix the variable in the positive form without the bar on it, or the negated form with the bar on it. So a clause is just a disjunction of literals. So here, as an example, x1 or not x3 or x5, that's what we're going to denote as a clause. Okay? And a formula in what is called conjunctive normal form. So that's where the CNF comes in again. So CNF is a conjunction of clauses. So it's an and of these clauses. So just as an example, let's take the same one we had before, and then we're going to and it with, let's say, x2 or not x3. Anyone lost so far? In some sense, yeah. Other questions? And then what we want to know about this formula is whether or not it's called satisfiable, which means that there is a way to set the variables of the formula such that the resulting formula evaluates to true or 1 or whatever you call it. So a formula is satisfiable if there is a way to set the variables to make the formula true. Okay. Is the formula right above it, the one in CNF, is that satisfiable? Is there a way to make that formula true? Yeah. What would be one assignment to the variable? Well, how about I set x3 to false? Well, then what is this formula? If I set x3 to false and every other variable whatever, is that one true? Yeah. Well, is this clause true simultaneously? Yeah. So this formula is satisfiable. What if so this one will still be satisfiable, but what if I change x3 to be just the positive form in the other clause? Well, what would be a satisfying assignment now? Yeah, so if I set x1 to true and I set x2 to true, then both of the clauses are true. True and true is, of course, true. So therefore, this formula is also satisfiable. What about this one? So I'm intentionally making this not work. What about that formula? Well, if I set x1 to true, actually no, this one will work. Yeah. So it's actually kind of hard to make instances that don't work. So this one is true. Why? Because you can just set x1 to true and x2 to false. Good. Let's see. What would be one that doesn't work? So let's try to make one that doesn't work. That's definitely unsatisfiable. So let's say that we want this. Okay, yeah, I got it. x1. It's easy with one variable. It's kind of harder with two. So, oops. There. So this one I guarantee is unsatisfiable. So if you set x1 to true, then what happens? So this one is definitely true, right? So then that one's true also. Well, in the other two, what do I need to set about x2? Well, if I pick the third clause, say that one, then I have to make x2 true because x1 bar is false. So that means x2 is true, but then I don't satisfy the fourth one. So in fact, this formula is unsatisfiable because I have every possible pair of either x1 true being the positive form or the negative form, and for x2. So this formula is unsatisfiable. So of course, some formulas are satisfiable, some are not. Okay? So of course, it doesn't seem very obvious that such a model would help us get other NP completeness results, but we'll see. And then we say a formula in CNF is in 3CNF. So it's in 3 conjunctive normal form if every clause has, without loss of generality, exactly 3 literals. Okay, so the formula from the one right above it, or either one actually, they're not in 3CNF as they are right there. Could I convert, say, that formula, the one we just showed was unsatisfiable, into 3CNF? Yeah, what do I do? Yeah, so like I can just repeat a variable or a literal here. So if I have the first clause, I can say x1 or x2 or x2. That doesn't change the trueness of that clause. I just have a repeated literal there. So we say that it's in 3CNF if it contains exactly 3 literals. If it has any clause with fewer than 3, then we could just repeat another or 2 literals until it becomes 3. Okay? Any questions about 3CNF? So then we say, finally, 3sat is the set of all formulas phi such that, phi is a 3CNF formula that is satisfiable. Satisfiable. So I'm deviating from CSE just a tiny bit, but it will be able to show that this is NP complete. But if I had an NP complete problem to work with, then maybe I could do a reduction to 3sat, and then I can then show that 3sat is NP complete. What 2 things do I need to show, though, to show that 3sat is NP complete? Show it's an NP and show that it's NPhard. So is it in NP? Oh, so what's the certificate here? Yeah, the assignment to the variables. And then I just evaluate the formula and then see whether it comes out true. So that's not very hard. So 3sat is in NP because the certificate is the assignment to the variables. I don't know what this is doing. Oh well. The little monitor up here is trying to make me record using the camera. I don't know why, but it's an NP, right? Because the certificate, whatever that is, the assignment to the variables, and I can check whether the formula is true or not. And if the formula says true, therefore the formula must be satisfiable. Okay? Any questions on that? But of course, the harder thing to do is to show that it's NP-hard. But that's what we're going to do here. And this will take us probably until the break to do, because it's a long. It's long, but it is technical, but it's very intuitive, or at least to me it is intuitive. but well, think about NP-hard. I need. It says that if I pick any problem at all in NP, and I can show that it reduces to this problem, then this problem's NP-hard by definition. But of course, if I had an NP-complete problem to work with, then I can reduce to. Do we have an NP-complete problem yet? No. So should I just start picking languages in NP and then reducing them to 3 set and then hoping that that'll be enough? No. How many languages are in NP? Infinite. Do you have an infinitely amount of time? Not yet. The heat death of the universe is not close enough yet. But we need a more general thing to do here. So it's what we want to show is that for any B and NP, that B reduces polynomial time to 3 set. That's what we like to show, and that would show as NP-hard. Well, there must be something that's in common with every problem in NP, every language in NP. What does a language being an NP mean? As a polynomial time verifier, what was the original definition? It had a polynomial time non-deterministic Turing machine to actually solve that problem, right? That's what we defined NP as, is this n time thing of n to the k. So maybe we can go off of that. Maybe we can say, oh, whatever problem that you pick, there must be this polynomial time non-deterministic Turing machine. And then maybe what we can do is we can model that as a formula. Okay? So if I can turn the computation of this Turing machine that I suppose exists, and I can make a formula based off of that, so that this formula is true if and only if the original machine accepts its input, then is that a reduction? Yeah, that's a reduction because I'm preserving the answer, remember? It accepts its input if and only if this supposed formula that I make is true. Okay. Any questions on the high-level idea? Well, so let's just write part of that down. So pick any B and NP. Then from that, there exists a Polytime non-deterministic Turing machine. Let's call it M for this language B. Okay, so whatever problem that I pick, whatever input that I pick and I feed it to this machine B, it behaves non-deterministically, but it always takes a polynomial amount of time in the worst case. Question: how many cells of the tape can I use? Can this machine use? Can it use infinitely many cells? If it runs in polynomial time. If it moved right every single time in the worst case, how many cells can I use if I run in polynomially many steps? Well, polynomially many cells of the tape. Okay? Well, let's see. If I have polynomially many cells that I could ever reach in whatever computation I consider, the screen back there is not matching these, so I was just making sure. So if I have polynomially many cells I could ever visit, and the length of the computation is polynomial in size, then maybe we have a hope of making this formula in polynomial time. So we're going to take another slight diversion and show you the high-level idea of how we're going to make the formula, but the formula is not going to actually look like this. So what we're going to do is think back to LBAs, where we had these two end markers, but we're going to look at what is called tableau of the computation. So here, what we're going to do is we're going to make a giant table, and we're just going to fill it with the computation one row at a time. So the way it's going to work is this. So at the beginning, we're going to put down the configuration of the machine at the start, which is Q0 and whatever the input is, let's say W1, W2, up to Wn. And, well, I don't know from this right now that how far this machine could ever go. So let's actually give it a certain polynomial, whatever it is. So say m runs in p of n time. So p is a polynomial in n. Well, here, I must have a lot of blanks afterward. And then I'm going to end mark it with these two special characters. So I'm just going to reiterate. The formula is not doing this. It's not making this tableau. But we're going to make a formula that is going to have the same behavior as the tableau. Okay, well, let's see. So we're going to basically do a simulation of the machine. And I know how far it could ever reach. So this entire length is p of n, all the way over here. It technically is not exactly p of n because I have these two n markers plus the state, but it's just minor details at this point. So we're just basically doing a computation of the machine here. Well, I don't know what it's going to do in the first step, right? It could change W1 to something and try to move right. I don't know what it's going to do. But so something's going to happen in the first step, and then something's going to happen in the second step, and then so on. And then at some point, we hope to see a Q accept, meaning that the machine accepts its input. So hopefully way down here, somewhere out here maybe, we see a Q accept, and we're done. And that would be the end of the tableau. Well, since it runs in P of n time, then the number of rows here is P of n. Well, at most, because it could run in shorter, but I guarantee is at most this number because I said by assumption it runs in that amount of time. So this is also P of n right here. So even though this tableau is really huge, it's still polynomial in size. It's p squared of n, but it's still a polynomial, which is all we care about here. Okay, so if we can make a formula that says that the first row must be Q0 followed by the input, then we say that the last row has a Q accept somewhere in there, and each line follows from the previous one, then if the formula is true, then we can figure out whether the machine accepts W in a polynomial amount of time. Because then we can just look and say, what are the true variables in this formula that we're going to make? And then we could just say, oh, it did this in the first step, then it did this in the second step. But the way we're going to make the formula is based off of the machine. So in fact, the formula is going to be true if and only if the machine accepts its input. Okay, well, let's see. we got to convert this idea, this big table, into a formula with these variables that have either a positive or negative forms, and but they don't know about these particular cells, right? They don't know what a pound sign or Q0 is, right? All they know is I'm going to be true, and I have a label for what my variable is. I know what the variable is, and I'm going to be true or false. That's all I know. So what are we going to need here? What we're going to look at is pick any cell out of here. We're going to let's just say that the cell contains some symbol L, some symbol. Then let's say that this symbol occurs in row I, for instance, and it occurs in row J. Then to make a variable here for that cell, we're going to make a variable called xijl. And then, so this is not going to be looking at the tableau. This is saying for all rows and columns that could be between the polynomial and 1, which is where we start from. So basically any row and any column. And then L can be any symbol, right? So any of the tape symbols of M. But it also could be any of the states. And it also could be the special symbol pound sign. Okay? So all we're doing is saying what can appear at every cell. So right now we're just saying anything can appear anywhere. So any of the symbols, any of the tape symbols of M, any of the states, and the pound symbol can appear anywhere in this tableau right now because we haven't made the formula yet. So, and L in the tape alphabet, union the states, union the pound sign. Okay, so what we want out of this is that xijl means in row I, column J contains that value L. That's all we're meaning right now. But we're going to actually make the formula in a bit. Actually, we might go over time on this one. So we might not get everything right before the break. But is the idea clear? Or unless there are questions before we get into the cool stuff. Yeah.
So every symbol on a tape is converted into this format.
Yeah. So these are Boolean variables.
So is that saying that symbol is on the tape or it's not?
No. We're making the formula now. So we're not going to be thinking of the tape anymore. We're just making the formula, and we want it to emulate the computation of M. So think of the construction of the supposed decider for ATM. We built it using a supposed decider. Here we're using a supposed machine for this language B, and we're going to emulate its computation. We're just going to, whatever input it gets, we're going to make a formula based off of that machine and that input. And this formula is going to be true if and only if that machine accepts that input at all.
So does that variable x, does that represent, when that's true in our formula, what does that mean?
That means in row I, column J, it contains that value L and no other values.
And if it's false, it doesn't contain that?
Correct, yeah. So there's another question, yeah. I'll continue though. Yeah. So the high level idea is we're going to make a little formula that says we have to start with the starting configuration, Q0 with W after it, with all the blanks after. Then we'll make a little formula that says the last row must contain a Q except somewhere.
When you say that means that you're assuming that it accepts, right?
No. I'm not assuming anything about the machine. But the formula is true. It is satisfiable if and only if. So there is an assignment to the variables if and only if the machine accepts W. I don't know whether it does. Right. So, but we're going to make a little formula that says the last row must contain Q except, because it has to. Then we'll say, there's one more, but it's a technical one. But the main one is that every row follows from the previous one by a transition. And that's all that we need. Yeah.
What's the input string is the formula?
So you're given, so think of like ATM as an example. You're given a machine and an input string. And so we're making a formula based off of that machine and that string. And the fact that we know in advance that it runs in this polynomial amount of time. Any other questions? Cool, let's get started. So, and you say, we haven't gotten started yet? But that was the main idea. So, but what was just asked here is like, what does this variable mean? So suppose we had, in the very first cell, in 1, the upper left, we had set to true with the pound sign, and we had 1, same cell, but we had Q0 in it also set to true. Is there anything that says currently that with the same cell with different values, one has to be true and all the others have to be false? Do we have anything that says that yet? No, we have something that says any of them could be true or any of them could be false, right? So we need a formula that says that exactly one of the values is set to true in every cell. So in every cell, there's exactly one value in there. It can't be the case that both of these are true, for example. So we have to, if we look at this formula, if I have these two variables set to true, then the entire formula is false. Okay? But if I have, for example, this one set to false, which it should be, then the formula is not currently false, but it could be false later. So how are we going to make this formula? Well, let's see. Gotta turn to my notes. All right, yeah. So this condition about having exactly one cell, one value in every cell, does that have to be true for every single cell in this tableau? But don't I want it to emulate a computation? In a Turing machine computation, could two values appear in the same tape cell? No. So here we have to make sure that this is true for every cell in the entire computation all the way through. Okay? So we're going to make a little formula here called phi cell, which just means this little formula is true if and only if there's exactly one value set in every single cell. Okay. Well, this has to be true of every single cell in the entire thing. So we have to say and over every single row index and every column index. Okay? So for every row and column index, so for every row I, every row j, this cell, row I, column j, must have exactly one value in it. Okay, well, how are we going to do that? Well, could saying exactly one value mean it has at least one value and it has at most one value? Is that the same thing? Oh, okay. I'm glad you're here to help me here. Okay. Well, so for convenience, let's call this set, the whatever can appear in every cell, let's call that C. Big C, the set of symbols that can appear in cells. Well, at least one of them is true means that there's a disjunction over all the possible values that can go in there. Okay, so if I have a disjunction of all those values and something else, then that must mean at least one of the values must be true. So if I look at this, which is, if I look at every single symbol in C, and I OR them all together, X, I, J, S, and something else that we're going to fix in a second, and that's the entire thing for phi cell, then could any of the variables in this first little part be, can all of them be false to make this phi cell true? Well, suppose that every single thing in here is false for this particular choice of I and J. Well, if this is ANDed with something else, then what is true here? That entire thing is false, but I just ANDed over all possible cells. So is phi cell false? If one of the I and J evaluates to false, then the whole thing, phi cell, must be false, because I ANDed them all together. So this just says phi cell is true if and only if every single choice is true, because it's a giant AND. Well, here, all we did is say at least one thing is true. Could all of these be set to true currently? Yeah, there's nothing forbidding me from doing that. So now we got to look and say there's exactly one value that's true, meaning that if I look at any two different values, both of them must be false. Or sorry, it can't be that both, it cannot possibly be that both of them are true. Okay, so if I look at these two right here as an example, then it can't be that both of them are true. Could both of them be false? Yeah, because some other value might occupy that cell. But it can't be that both of them are true. Okay? So let's see. How are we going to do this? Well, I got to look at any two possible values, different values, and say that it can't be that both of them are true. Okay? So how are we going to do that? Well, I'm going to say that for any two values at all, it has to be true for any two values, so I have to do a giant AND here. So I pick, say, symbol S, symbol T, in this set of symbols I can use, such that they're different. I pick any two that I like. Then it can't be that both of them are true. Okay? Well, that must mean that it must be that this one is false or the other one is false, or both are false, which means we got to do this. So xijs bar or xijt bar. Drop mic. So let's recap. So because this is actually one of the harder formulas. The other formulas are a lot easier to work with. And we'll take a break after when I explain this. So we have to have exactly one value in every single cell. So we're saying that this must be true for every row index and every column index, which is what the outer giant AND is for. The inner one says that we must have at least one value in this particular cell, and at most one value in this particular cell. The first one says, this little bit right here, there's at least one value that's true, because if all of them are false, then this little part is false, which means the entire formula, phi cell, is false. But then for the second one, it can't be that two of them are set to true. Any two values are set to true. Well, if I pick S and T, for example, and I set both of them true, then this little bit right here, false or false, is false. Well, if I'm doing a giant AND right here, this whole AND must be false. But then that must mean the whole formula phi cell is false too. So that means at most one value is true, and at least one value is true, which means there's exactly one value true. Questions about this before we break? A much needed one. Cool, let's take a break.